my talk is devoted to the generating the sequences of pseudorandom numbers that produced by the elliptic curves over the ZPM's power. The sequences of pseudorandom numbers have many applications, both in pure and applied mathematics, and also have its applications in modeling and modeling the real processes. But the big interest for me is to apply these sequences to the cryptography. There are large numbers of methods for generating such sequences, and the one way of classes of producing the pseudorandom numbers is generations using the finite fields arithmetic and the finite rings of residue classes modulo positive integer n. So we study the generators of pseudorandom numbers using the elliptic curves over the finite field. And the good start to study the generations of pseudorandom numbers using elliptic curves is the paper of Igor Sparlinsky that you can see on this slide. Okay, so let E be the elliptic curve defined over the field Fp, given by a Weierstrass equation of the following form, where the coefficients A1, etc., and A6, such that the partial derivation of function f presented here, that this function don't become zero simultaneously at the points of the curve E. Of the points of the xy of the curve E over the algebraic closure. For the case P is greater than 3, the previous equation can be deduced to the next form 1. For the sum AB with this condition. We recall that the set of points of curve E together with point at infinity forms the abelian group of order which satisfies the following inequality. For the point Q of elliptic curve E, we use this notation to denote the elements of the curve, of the elliptic curve. Well known that elliptic curve have a rich and beautiful history, having been studied by mathematicians for over 100 years. Theory of elliptic curves has many applications in classical mathematics, but after that, in cryptography, the Koblitz and Miller independently proposed to use the elliptic curves for designing the public key cryptography systems, and for today there is a big abundance of researchers devoted to security and efficient implementation of elliptic curves in cryptography. So the main purpose of our research is to receive an algorithm for generating the sequence of pseudorandom numbers feasible for cryptographic applications. So let EM be the elliptic curve defined over ZPM's power and set of points x, y satisfying to the congruence 2. And let n of EM be a number of solutions of the congruence 2 for M that is equal to 1 with condition of coprimes y. And by the theorem of Hasse, we have the following with the constant in symbol O. So we have the next definition. Let the point x0, y0 be the initial curve EP defined by the congruence 1. Let p is greater than 3 be the prime number, and that is greater than 3 be the nature, and let yi of t are the polynomials over z pm's power that are the solutions of congruence 2. So the normalized sequence yi of t divided by pm's power calls the sequence of pseudorandom numbers associated with elliptic curve. We proved the following theorem to present the solutions of congruence 2. And we prove that the following congruence 3 has two incongruent solutions modulo pm's power over for every positive m. So indeed, for p that greater than 2, the solution of the congruence 3 with m that is equal to 1, such that y and p are coprimes, we can continue to solutions modulo pm's power for every m that are equal to 2, 3, etc. uniquely. Also, we prove the following lemma that where we obtain the representation phi of t that allow us to construct the solutions yi of t, the points yi of t that are together with points x, y belongs to the elliptic curve 2. And also we obtain the following corollary in the conditions of lemma 2, when we obtain the p-adic description of the solutions of the following congruence. And we have the remark that says that just note that the sequence y of t defines by selection of initial point and by selection of one of possible solutions y1 of 0 or y2 of 0 of the congruence 2. Also, we obtain we prove this theorem 1, where we obtain the number of solutions x, y of the congruence 2. So we proved that the following asymptotic formula holds with some absolutely constant in symbol O. Also, we obtain the following theorem that allow us to obtain the discrepant function to estimate our constructed sequences. So using this theorem allow us to estimate the discrepant function for the normalized points y of t, and also the description of k-dimensional points. So in particular, the estimate of, we obtain the following upper bound for the discrepant function d. And that says that the sequence of pseudorandom numbers yi of t generated above pass the test on equidistribution and statistical independency that are the main properties for cryptographic applications. So we prove that such sequences can be used in cryptography. Also, we have some remark that we can define some group operation on the set of sequences generated by the selection of initial points y0, x0, y0, and some value I, as we can see here, such that by two initial points x01, y01, and x02, y02, we calculate another one initial point x03, y03 from the elliptic curve EP, by which we calculate the pair of solutions yi3 of t of the congruence 2. Using the results that we obtained, we construct the algorithm to generate the sequences. So the step-by-step algorithm of constructing the sequences of pseudorandom numbers associated with elliptic curve over finite ring ZPM's power for prime P and natural M can be described by the following way. We choose the initial point x0, y0 from elliptic curve and use the condition that y0 and p are coprimes. I test for the point of elliptic curve produced by the defined by the following congruence over ZP with non-quadratic residue minus 3a. We construct the point x of t, y of t, which belongs to the elliptic curves over ZPM's power in the following way. So we select initial point xy, x0, y0 for the non-infinity point component y0. Then we calculate x of t by the following congruence, and then we calculate part yi of 0 for y that are equal to 1 and 2 as the solution of the following congruence. We use the Taylor series for the function of omega and the point omega that is equal to 0 in the following way. Here, x0 prime is the multiplicative inverse for the x modulo Pm's power for x03 plus a x02's power plus b. Next step, in the right side of the Taylor series, we put omega spt and then modulo Pm's power. We construct the following polynomial phi of t in the following way, where functions of I of x0 are the integer value functions with the following presented here conditions. The next step, these polynomials phi of t and the solutions yi of 0, we use to construct the following representations of solutions yi of t, or for the representations of the components y of t for each I that are equal 1 and 2, which produce two sequences of pseudorandom numbers, y1 of t over Pm's power and y2 of t over Pm's power with the Pm minus 1. From theorem 2, we also obtain the following estimate as a corollary of obtained representations yi of t. And so we can say that the constructed sequences of pseudorandom numbers associated with elliptic curve passes the serial test on pseudorandomness and therefore may be used in cryptographic applications. Next research that we that we done is research the pseudorandom numbers generating unit circle. So now using the obtained by us for elliptic curve over the finite field f p square that we obtain above, let's see how to construct the sequences of complex pseudorandom numbers which are the equidistributed in the unit circle. Indeed, let's see the set of points x and y which satisfies the following congruence, where a and b are the Gaussian integers, p a prime rational number, and with the condition p is congruent to 3 modulo 4. Such p state to be prime in the ring of Gaussian integers. In the same way, to the first part of my talk, we can obtain the description of solutions of the following congruence and the related sequences of pseudorandom numbers as the sequences of complex numbers with norm that is less or equal to 1, that is the sequences of complex numbers on the unit circle. Also, we have the following, and for complex zeta in the circle, in the unit circle, let's define n of zeta and consider the sectorial region pi, sectorial region p as the following, presented in 1. Let f denotes the set of regions, such regions for possible psi and phi. We say that the sequence of complex numbers Zn be the pseudorandomness in the unit circle if there exists a deterministic algorithm that generates such sequences, and such sequences be the equidistributed in the unit circle and be the production of the sequence of independent random values. The equation of equidistribution of such points in the unit circle can be resolved using an analog of Turner-Josh-Koxma inequality that have been obtained in our work presented below. We obtain the following theorem, where we obtain the upper bound for the discrepant function Dn. In our case, the discrepancy can be estimated as we can see here, when n is a number of points y of t. Also, here we should say that in a classical way, the discrepant function considered on the some interval, and the equidistribution of the sequences means that the count of points that can be false in such intervals depends only on the length of such subintervals, but does not depend on position of these subintervals in the last one interval. But in a way of unit circle, the equidistribution of points depends only on the size of sectors, the count of points that can be false in some subsectors on unit circles depends only on the size of such sectors and does not depend on the position of sectors in the unit circle. And such discrepant function for such points we call the angular discrepancy. So in the first case, we call discrepant function as interval discrepancy, and in this case of unit circle, we call the discrepant function as angular discrepancy. And so we obtain such bound, such estimate, upper estimate for the discrepant function that say that the sequences the sequences of points from the unit circles pass the serial test on equidistribution and statistical independency, and so such sequences also can be applied in the cryptographic application. So that my time, I have some minutes, but I end of my talk now.